Hey, so here are the answers to the stations. I might be a little addicted to making these videos now. So we've got three different scale situations. We've got Gregory, he's standing on the scale every single time. Jasmine's applying a force to him on B and C, but not A. So we're gonna make a couple of free body diagrams. We know that Gregory doesn't move, and so he always should have a balanced, like, net force of 0. So we're going to start with free body diagram A. The scale always reads the normal force, my friends, and the only other force acting on him is the force of gravity. So he should have 481 newtons going up for normal force and going down for force of gravity. If you need to write that down, pause it. I'm going to erase it. Okay, now what we know about Gregory is that his weight is 481 newtons. And I'm going to write FG. Oops. Ah, for crying out loud. Okay, so that's FG. We also know that the scale is reading 612, so his normal force right now is 612, which means Jasmine must have pushed down on him. And that means force of Jasmine, which I'm going to write as FJ, is pointing down. And that's going to be equal to whatever 612 minus 481 is. That's 119 plus 12, 131? Yeah, 131 newtons. Okay, so we've got 131 plus 481 is equal to the 612, because it has to balance out because he's not moving. All right, I'm erasing that. Hope you guys enjoyed my mental math. All right, so for the next one, again, we are doing Gregory's force of gravity is 481. His normal force is written on the scale, 397. And then Jasmine must be pulling him up, and it's going to be 481 minus 397, which this one I remember, 84 newtons. So that 397 plus the 84 has got to equal the 481. And that has to be true because he's not moving, so the forces pointing up have to balance out the forces pointing down. Okay, I'm getting rid of that. I don't know why I feel like I have to give you guys a heads up, because you could always just rewind, but hey, whatever. All right, last one. What's Gregory's mass in kilograms? We know force of gravity equals mg. We know his force of gravity is 481. We know his mass is m, and then g is 10. We really could do negative 481 and negative 10. Doesn't matter. So we divide by negative 10, and we get that his mass is 48.1 kilograms. There you go. All right. The next one, Station 2. So this one we have Ruthie, and she's pulling a 15 kilogram box to the left. The force of friction acting on the box is 39, so that's going to be pointing to the right. And Ruthie is pulling to the left with a force of 111. Now what you'll notice, it says Ruthie lets go of the box at point 2. So that means between here and here, there's no force of the pull. Okay. We're going to draw the free body diagram. So between 1 and 2, that's when there is Ruthie's pull. So let's put that on there. F Ruthie is 111 newtons. Super. This way, F friction is 39 newtons. Wonderful. Okay, pointing down is going to be our force of gravity, which is 150, because that's mass times g, mass times 10, so 15 times 10. And then pointing up should be normal force, which is also 150. So I'm going to make this a little bit shorter, this one a little bit shorter too. So I want to make sure, you can't really, this one's not great. I'm going to adjust the size of my arrows. We're restricted down there. So, all right, this can be little. This will be almost as big as those ones. Okay, so these two are supposedly the same size. This is a little bit smaller than them. This should be the smallest one of all. All right. The next one should look pretty much the same, but the only thing that changed is that Ruthie let go of the box. So we still have a normal force supporting the box. We still have a force of gravity pulling it down, and we still have force of friction. We just don't have anything pulling that box anymore. So I'm going to copy down all of those. So a lot of people are having trouble with the fact that the box is still moving. It's true, but if you look at the net force, our net force is pointing this way, and the D is pointing that way, which means that it should be slowing down, which it is. Well, you can't really tell, but it is this V. One of the problems, I don't know if the problem that I took this from actually asked you to solve for V. This V, if you solve for it, which I did because I'm a physics nerd, is like 3 point something. I think it's 3.84. I don't know. But anyway, so it does end up slowing down. So you would have to just figure from 2 to 3, it slows down. That's all. All right. So now I'm going to go to the next one. All right, Junior. Junior's sliding a box down the hallway, and it's 25 kilograms. And so when the box is already moving, he's pulling with this 50 Newton force that they show us, and there's a friction force acting on it as well, and it's moving to, to the right. So we know our force of friction moves to the left. I'm going to draw a force diagram. So here we go. I'm starting with my FG. My FG is going to be 25 times 10, or 250 newtons. All right, so for this one, what I'm going to do is I'm going to draw just the horizontal and vertical components. I'm not actually going to draw that 50 newtons. So this is F pull in the Y direction. That is 30. So I got that from here. And then we're going to have this 40 F pull in the X direction. We're running out of room. That doesn't look great. Huh. Oh boy. All right, one more time. Sorry, you have to sit through this. 40 newtons. Close enough. Okay, so we have to also include the 45 friction, which is that way. F equals 45 newtons. And then the last thing we have to do is include normal force. So we should know that the vertical net force of this should be 0, and we should know that because it's moving across the floor. It's not going up or down. So the up or down vertical net force should be 0. So currently we have 250 newtons pointing down and 30 newtons pointing up. So in order to balance those out, we have to have another 220. So the normal force here is 220 newtons. And I know that screws some people up. A lot of people want to say it's 250. It's not. Think about the scale problem where the force of gravity and the normal force are not actually the same. So when we look, we already answered the vertical net force was 0 newtons. Not on, but 0 newtons. The horizontal net force, we've got to the left is 45, to the right is 40. So our horizontal net force is -5 newtons. The last one, this should say box. Who knows why it says book? The box will either speed up, slow down, or move at a constant speed. So we can see that our horizontal net force is -5, so that's to the left. We know the displacement is moving to the right, so it's going to slow down because F net opposes the motion. If F net went to the right, then it would be speeding up, but it's slowing down because F net opposes the motion. Okay, next, and then I'm going to end this video and make a new video for the next ones. Oh, for crying out loud, this one's hard. Okay, so we've got a 510 gram soccer ball, so that's 0.510 kilograms. That's the mass, and it bounces between two scales. We're assuming drag when it's moving, and we're drawing the force diagram. So here we go. I'm going to draw, oh, wait a minute. I always end up, well, we'll see what happens. So we're going to do FG equals, what does it equal? 5.1. Okay, so that's what, because we do mass times 10, here's the mass, multiply by 10, move that over 1, done. All right, in part A, it's moving up, so that means drag will be moving down. So we do a little FD equals 2.0 newtons. And that's it. And people keep wanting to draw something up this way, but nothing, there's no applied force. If you look at this ball, nothing is touching it. It's in midair. So when something's in midair, we've always got force of gravity. And if we're doing force of drag, then we use force of drag. And that's it. So there might have been something that threw the ball up in the air at first, probably. But that's done now. It's not touching it anymore. No more force is being applied to that ball. Okay, the next one. Still force of gravity. Pointing down. And the other thing, we've got this scale up here, and it reads 8. And that scale, that ceiling is making the ball want to turn around and go back down. So it's actually pointing down, a normal force that points down. Crazy. So that normal force is going to be the 8 newtons. So we've got force of gravity pointing down with 5.1 newtons, normal force pointing down with 8 newtons. Think about if you hit the wall. If you jump up to the ceiling, you hit the ceiling, it's going to knock you back down. It's not going to keep you going up. Okay, next one, C. Oh, and there's no drag because it says V equals 0. Okay, it's only got drag when it's moving. The next one, we've got nothing reading on the scale. We've got it moving, and it's moving down, so F drag is going to be up. Our FD equals 2 newtons. I'm going to have to erase that when I go on to the next one. And then going down, we've got our FG of 5.1. Nothing's being applied. There's no normal force, not touching anything, so we are done with that. The last one, we've got our good friend 5.1 newtons. Oops, that's our FG. And then we've got something going up. So it's on the scale, it's pointing up. We've got a normal force of 14. And when we look at this, we must realize that the ball is going to end up moving upwards because its net force is pointing upwards. So yeah, I know it's at rest, technically, but it's not going to stay at rest, and that's why we can have something moving upwards. All right, I'm going to be back with stations 5 through 8.